Hey everyone, welcome to Math 111 with me, Matthew Keeling. So, we're going to try some things out. Right now I've got a big old chalkboard on order. Once that comes here, we may change up the way I do these lecture videos. But for now, though it's pre-written out on this paper, we're just going to scroll through and we'll try and get it done pretty nice and painlessly. So, obviously, this is a video, so the nice thing is you can pause it. You see something on there that you need to write down, pause it, write it down, however it goes, rewind. This is as flexible as you need it to be. Okay, so in mathematics, we talked in the previous classes, talked about all sorts of different things, equations, problems, just basic algebra things, inequalities. What this class really focuses on is the idea of a function. And before we can talk about a function, we need to talk about a relation. So in mathematics, a relation is any set of ordered pairs that we typically consist of an input and an output that we write as x, comma, y. Okay, we've seen these before, ordered pairs. We've plotted them on graphs and stuff and so forth like that. So this is a relation, just pairs some input with some corresponding output. Okay, so we can have names and heights, right? Social security numbers and their person's age, or x and 3x plus 1. Okay, the problem with relations is they don't have a lot of structure. So, All right. Go. Okay. Problem number one figured out. Since these don't have a lot of structure, what we do is we introduce some structure, and that creates a function. So in mathematics, we say that a function is any relation such that for every input, there is exactly one output. Okay, that's very important. For every input, there's exactly one output. If there's an input that has no output, then that means it's not really actually an input. Okay, and we'll talk about that in just a minute when we talk about the inputs and stuff like that. But every input, everything that goes into this function has exactly one thing. It can't go to two things at all. That creates a problem with our function. Okay. So if we look at the relation back here for three examples, right? Take a minute and think to yourself, pause the video if you need to, which one of these three are or are not a function. Look at each one and decide, is that a function? So that would mean that every input would have exactly one output. So go ahead, pause the video now. Try and figure it out. I'll wait. Back? All right. So we look at name and height, and we think about that. Two people could have the same name, and yet they could be different heights, which means my name is Matt. It's a pretty common name. I bet you there's another Matt out there, and I bet you they don't have the exact same height as me. So I mean, the one input of Matt would have multiple outputs. Even if you went further out to say my full name, right? My first, middle, and last name. I actually happen to know for a fact that there's a man in England by the same name. He's actually a math professor. It's a pretty fun world. And we are not the same height. So even if you go all of my names, there's somebody out there with the exact same three-name combination that has a different height as me. So, not a function. Social security number and age. This relies on the fact that social security number is a unique identifying number to every single individual in America that is issued a social security number. So that means that number applies to only a singular person. That means that person has one age. Now, if you want to say, well, what about their age today versus tomorrow? They have birthday, it changes, right? But what this is referring to is more of a singular moment in time. Grab it. How old are they? And x, 3x plus 1. So this is something that we're going to deal with more in this class. It's something that we're probably a little more familiar with. For any number that you put in for x, you're going to take that number, multiply it by 3, and add 1. If I multiply any number by 3 and I add 1 to it, I'm only going to get one thing back. I can't multiply 2 times 3 plus 1. It doesn't give me, say, 7, but also negative 13. So these last two are functions. This first one is not. Okay? So as we kind of go through, we're going to kind of focus a little bit more on this relation here. Okay? So in the past, the way we would represent this relation is we would use an equation. We'd say y equals 3x plus 1. Okay? The problem with this is, and you're going to see as we go on through the term, we're going to have multiple different functions that we're dealing with at the same time. And so rather than having, say, y equals 3x plus 1, and, I don't know, y equals 5x, and y equals negative 2x minus 3. Right now we just have y equals y equals y equals, right? Those are terrible y's, but hey, get the point. And so to help avoid that confusion of, well, which one are we talking about? So you say, what's the slope of that equation, right? There's 3 there. So what we use is we use function notation. Function notation is a very simple way that we can give a function a name, also clearly be able to interpret what the input is, and see that output, okay? And the way we do that is this base general idea right here. F parenthesis x, close parenthesis, equals y. And the way we say that is we say f of x equals y. So our f is our function name. We typically will jump to f, g, and h for the function names, just the same way as for variables we use x, y, and maybe z. Okay, x represents our input, just as it did all the way up here, and y represents our output. Okay, so pretty nice and easy. So with this function here that we're dealing with, this x and 3x plus 1, instead of the old way of saying y equals 3x plus 1, with function notation, we replace the y with f of x. Notice y equals f of x. And so what we can do is instead of y equals 3x plus 1, we get f of x equals 3x plus 1. Okay? So that's a nice jump start on function notation. For more on function notation, more examples, there's going to be an examples video for you guys late that'll be posted separately to this. You'll see another link down there for it. Go ahead and watch that. If you want to watch that now, if you want to wait a minute, you can. Now, with functions, there's actually 4 different ways that we can represent a function. Okay, the first way is verbal. So for our function here, right, f of x equals 3x plus 1. The verbal representation of this function would simply be 3 times x plus 1. Or you could say 3 times a number plus 1. Any sort of variation that is just simply a verbal description of what the function is actually doing. Okay. The second one is numerical. So numerical just simply means where you're dealing with some sort of table. Now notice the way I've done this table, maybe a little different, right? And if I do this horizontally like this, or if I did it vertically, it'd be the same thing. But instead of an xy table, I have an f of x table. So what this is saying is we're looking at if x is negative 2, then f of negative 2, because x is negative 2. So f of negative 2 would be negative 5. And so we get this little numerical table here. Now, when we're looking at tables, the problem with that is we don't know what happens between these. So if we're told that this function is linear or quadratic or any other thing, we can then use these points to help create the equation of that function, which we're going to talk about in just a minute. However, if we're not told any more information other than here's this function f of x that has this table, we don't really know anything more than just these points. So we got to be careful we don't kind of interpret what happens in between there unless we're actually given the information for what happens between there. Okay. The third way is the most common way and the way we're probably going to deal with it the most in this class, and that is the symbolic representation of a function. So that is our good old-fashioned function notation, f of x equals 3x plus 1. And lastly, graphical, which is pretty simple. It's a graph. So here's our graph of this function here, 3x plus 1, crosses that horizontal intercept, or vertical intercept, sorry, y-intercept of 1, right? It has a slope of 3 over 1. So pretty easy, okay? If there's any other question on that, post in the discussion forums. We will kind of break these down. I'm going to create a discussion forum for each video so we can post distinct questions for that video. So go ahead and post in there. All right. And again, you want more examples and work with function notation that'll also kind of do a little bit with some of these other forms. Okay, go watch that function notation examples video. You've dealt with function notation before and you feel like skipping that, that's fine. You can always go back and watch it later. All right. Cool. So we've defined a function as any relation such that for every input, there's exactly one output. Okay. Now we want to be able to talk about those inputs and outputs in a little more concise manner. And the way we do that is we define some different terms. So we say that the set of all inputs that are valid and meaningful is called the domain. So those two words, valid and meaningful. Every input has to satisfy both of these two conditions to be a part of the domain. Okay? And so valid is really simple. Valid just simply means that it works in the function. So if I put that into the function as an input, I get something back out, right? So that was what I was talking about before, where if you have some sort of an input that doesn't give you any sort of an output, then it's not actually an input of the function. It's not a part of its domain, okay? So for example, if f of x is the square root of x, okay, 25 is a valid input, since f of 25 is the square root of 25, and that's 5. However, negative 25 is not a valid input. Since f of negative 25 is equal to the square root of negative 25, that's not a real number, okay? For the majority of this class, we're only going to deal with real numbers. I know complex numbers exist, and we can deal with those at later times, but for now, we're just going to stick with real numbers, okay? Meaningful, now that only applies when our function is some sort of a model to a situation or some sort of a context, okay? And it just means that both the input and its corresponding output makes sense in the context, okay? In other words, if we have some function that takes inputs of time and outputs, say, the distance you've driven, we can't really talk about negative time, right? Negative 5 minutes doesn't really make any sense, okay? Another very common one is in the example here, right? I said getting over 100% of something used, right? If our function tells us what percentage of something is used, we can't say that 110% of this object was used. Another thing is when you throw something up in the air, right? Now, if I were to let this pen hit the ground when I just threw it, we could model that actually with a quadratic function, which we will absolutely do. But that pen would never just start burrowing into the ground. And so we would want to make sure that we cut off the inputs or the domain of that function at the point where the graph hits the x-axis or hits a height of 0. Because anything beyond that would have a negative height. In other words, the interpretation in the context of the problem would be that it went up in the air, came back down, hit the ground, and continued to dig a hole into the ground, which doesn't happen when we throw a pen in the air. So we want to make sure that things are valid, they work, meaningful, they make sense. Now, when we say make sense, that doesn't mean that it makes practical sense, it means it makes mathematical sense. In other words, it is possible. Selling things for $0, not a very good idea. It doesn't make sense to do as a business. However, mathematically, it makes absolute sense because we can physically do things, sell things for $0. Okay? So that's domain. Set of all inputs that are valid and meaningful. Then, the set of all corresponding outputs is called the range. Range is very simple. It's just our corresponding outputs. Okay? Now, if we're thinking of this function as a function graphically, domain is our horizontal axis, our x-axis, if you will. Okay? In other words, it's looking at that x-axis and saying what values on that axis give us some point of the function. And range is simply the possible values of the y-axis. So if I'm looking at, say, some function, let's say, I'll just kind of give us a little graph here. Say my function looks something like this. Well, unless we have some sort of a symbol, we assume that it goes off forever, okay? So our domain, the possible x values, we see this goes off forever that way, goes off forever that way. So our domain would be everything, right? Negative infinity to positive infinity, everything is included. But our range, we would see the lowest value is whatever this point is here, and then it would go from there to infinity. And so we would want to make sure that we're able to write that out. And now how do we write those out? So those are some intervals of numbers, right? Negative infinity to infinity, right? Whatever this is, let's just say it's 1, right? So 1 to infinity, okay? Previous ways some people have written these things out, we've done intervals, is represented using a number line, using either open or closed circles like this and shading the desired regions, right? We can use inequalities. So this is all talking about the same set of numbers from negative 3 to 5. We are not including negative 3, but we are including 5. Right? Using inequality, to be negative 3 is less than x is less than or equal to 5. Okay? And then a similar thing to inequality is something called set builder notation, which some of you may be experienced with, some of you may not. And what it really has, it has the inequality notation in it with these kind of curly brackets, and then this x and a bar. And what this then stands for is it's the set of all x such that negative 3 is less than x is less than or equal to 5. Okay, so it's just saying it's the collection of all these x values that fall between negative 3 and 5, including 5. Okay. Now, these are all okay for an interval like this, something really small, right? They're just a singular thing with a start point and an end point and everything in between, okay? But what happens, we get more complex sets, right? When we get sets that start, end, start, end, start, end, we don't want to have to do a bunch of different inequalities or do this giant number line or this giant set builder. So what we use instead is we use interval notation. Okay? Interval notation is what we will use for the entirety of the rest of this class and pretty much for any math class you take from here on out. So make sure you learn how to do this, right? It's pretty simple once you figure it out and not too bad, okay? So interval notation is a way to write a continuous or unbroken set of numbers, such as this right here, right? There's no gaps in it, by giving a starting and end point along with the appropriate end symbol. So our end symbols are these here. Now, if we use inequalities, less than or greater than or equal to, right, a solid circle on the number line, those are the same as a bracket. Okay, and what that means is we're going to go up to that value, and we're going to include that value, right? So here with 5, we see we would want to have a bracket there because we go all the way up until 5, and we actually want to include 5 in that, okay? Now, less than, greater than, or an open circle, we use parentheses with interval notation. And that means we're going up to or down to, but we are not including, such as with this -3. Okay? And you can mix and match. You can have one side have a bracket, one side have a parentheses. It doesn't have to both be the same. So this -3, what this is saying, we are getting infinitesimally close to -3. We aren't actually touching it. Now, that is different than saying stopping at -2, because there's infinitely many numbers between -2 and -3. Right? Think about -2.5, -2.9, -2.999999, right? So we want to actually represent this going all the way down to -3 and stopping there, okay? So for that, we'll jump down here to this example. Okay, so this right here is the same number line that we have here, right? And the way we would write that interval is our starting point would be -3, smallest value. Our ending point would be 5. And we want to have, since we aren't including -3, we'd have a parenthesis on that. Since we are including 5, we have a bracket on that. And as you can see here, that's exactly what we have. Okay. Now, if we look over here, this is -1 all the way to infinity. We're including -1, so that part's easy, right? That's our starting point, the smallest value. So we're going to start with -1 and have a bracket because we're including that value. Now we go all the way up to infinity. We keep going. So what symbol would I use on that, right? If you read this, right, you can probably already guess. But because infinity is not actually a number, it's an idea, we never include infinity. We always use a parenthesis with infinity, okay? So no matter what, whether it's positive or negative infinity, we are always going to use a parenthesis. So for something that's, say, all real numbers, or negative infinity to positive infinity, we would write that interval simply as parenthesis, negative infinity, comma, infinity, close parenthesis. Okay. Now, what if two sets need to be joined as one? Okay. If we look at this example here, right, which is the same one here, including -2 up to 0, but not including 0, then starting again at 1, but not including 1, and going up to 3, but including 3. So we've got two separate unbroken intervals that we want to create one set of numbers. The way we do that is we simply write the interval notation for each piece, and then we use this union symbol, which is just a large U. That's all it takes. Okay? So this first one here goes from -2 to 0. We include the -2, so that gets a bracket. We don't include the 0, so that gets a parenthesis. Okay? Then we have a gap. So anytime we have a gap, we put our union. Okay? So we'd have -2 to 0 union. Then our next piece starts at 1, but doesn't include, so we use a parenthesis. And that goes all the way up to 3, which we include, so we would use a bracket. Okay, and we end up with our interval notation that looks like this. So we start at -2, including -2, up to 0, but not including 0. Then we have our union. Start back at 1, not including 1, up to 3, including 3. Okay, so there's a little how-to on interval notation. Trust me, we'll get plenty of practice on this. Okay, you'll get some on this first homework assignment. So make sure you guys go through and are very, very, very comfortable working with this. Okay. For more examples of some interval notation stuff, but along with domain and range specifically, go and watch the domain and range examples video. Okay. So that is it for our first lesson. Congratulations, guys, you made it. Hopefully this video is okay and you guys are able to make out everything that's written up on here. If not, let me know. If I need to, I will go through and scan these and post them if I can. But yeah, communication is going to be the key this term, right? This is something that's new for all of us, the way we're doing this. I'm trying not to do this like a online 111 class. I don't want to put everything on you to learn because you guys signed up for a face-to-face class. So I want you guys to see my face some. So if you guys have any comments, questions, or concerns, feel free to email me, post in the discussion for this lecture, or whatever you need to do. Okay? Have a great day, guys.